Okay, let's get started. Um Hi, everyone. This is Upmanu Lal at Columbia University. Welcome to the webinar today, which is co-organized by Quasi and Columbia Water Center. It's related to our NSF Water Sustainability and Climate Project called America's Water. And we've had a series of people in this webinar series so far, and we'll have several more coming up. Um, and thanks to all of those who have joined. Today, the topic is on climate change, water resources, and electricity provision in the West. And the presenters are Matthew Bartos and Mikhail Chester from Arizona State University. Um, I I've only had a chance to look at some of their work, and it's very interesting connection from climate all the way through to urban infrastructure, specifically linking water and energy. So I'm very keen to hear their talk. And the way we have usually done this is that the presenter goes through and presents, and then questions are asked in the end by typing them in. One of the things that may be helpful is that as you listen, if questions occur to you, please go ahead and type them in into the chat window, and that will help us move to the question part of the presentation faster than has happened sometimes. Again, thanks very much. Welcome, Matthew and Mikhail, and let's turn it over to you.
Thank you, Manu. Thank you again for the opportunity to present to the Kawasi group. I am looking at the list of participants and I recognize some names, so good to connect with you all. And for those of you who I haven't met, looking forward to connecting our work with your interests. So what I wanted to do by the way, I'm Mikhail Chester. I'm an assistant professor at Arizona State University. I've been there for about 4 years. And my work largely revolves around two sets of questions. The first is I do a lot of work around life cycle assessment of infrastructure systems, a heavy emphasis on transportation. The other half of my work, which is what I'll be talking about today with Matthew Bartos, is on the impacts of climate change, particularly extreme heat or heat waves, on infrastructure and how it creates vulnerabilities in infrastructure. So today what we wanted to do is focus on work that Matthew has been leading on the impact of climate change on electricity provision in the West. But what I wanted to do first was start with just a short overview of the research questions that we're thinking about, just to give you a sense of how the pieces connect to each other. And then what I'll do is talk about that for about 10 minutes and then hand it over to Matthew for the remaining 30 or 40 minutes to talk specifically about the details of the work that we've been doing around electricity provision in the West. So, the sort of series of questions that we are addressing, again, are largely related to heat. So when I say climate change, we're largely focused on heat issues in the Southwest. So you'll see a lot of discussion about Los Angeles and Phoenix, which tend to be the two big cities in the Southwest that we focus on. But we've been addressing through a series of projects, probably 4 or 5 projects that are currently active, questions related to how the design of infrastructure is vulnerable to climate change and how that vulnerability affects people. The second being how more frequent heat can, my audio is patchy. Okay, so I'm seeing people say that my audio is patchy. I'm on a landline, so I'm not sure what I could do differently. So I'm going to just keep going here because I'm too close to the mic. I'm not too close to the mic. So I'm going to keep going. I don't know if there's anything I can do with my audio at this point. So the second set of questions that we are addressing, let me try talking directly into the handset. Okay. Can you all still hear me? Okay, so I'm going to keep talking right into the headset. All right. So the second set of questions that we're addressing are related to how extreme heat or heat waves can create vulnerabilities in both water systems and electricity systems down to the component scale, and then how these vulnerabilities can potentially propagate across systems. And the third are related to the impacts of extreme heat or heat waves on electricity systems, which is what Matt will talk about a little bit later. So to start, the graphics are not appearing on the PowerPoint here. We have developed a series of studies of air conditioning availability, access to public cooling centers, as well as the thermal characteristics of buildings and how the design of infrastructure creates social vulnerability to heat. So the questions that we're raising here are related to how we've designed cities based on what I would say are kind of historical exposure to heat, and now we're experiencing more frequent heat waves in the Southwest. And do the design of our infrastructure, particularly access to cooled space, contribute to social vulnerability? So you might suspect that there are areas of the Southwest, areas of cities, particularly neighborhoods and cities in the Southwest, that have been designed one way or another in terms of the thermal characteristics of buildings, the penetration of air conditioning, and then access to both county cooling centers as well as publicly cooled space that may result in more or less exposure for certain vulnerable segments of the population. So that's the first set of questions that we're asking, which are not directly related to water. In these questions, we're partnered with folks at UCLA, a medical doctor and public health folks at UCLA who are thinking about social vulnerability to heat. And what we're trying to do is create this sort of socio-technical assessment of heat vulnerability based on the design of urban infrastructure. On a separate set of questions, will more frequent heat waves create vulnerabilities in water electricity systems? What we're doing is relying on or leveraging this concept of the water energy nexus, which we've done a lot of work on in Arizona. So this figure showing the life cycle of water from extraction through use and treatment, potable use, and then wastewater treatment, and the embedded energy associated with each of those stages. So you can see more and more energy is embedded along the way. And what we're doing is we're asking questions here of, and again, I apologize, the graphics are not appearing. Here we go. Okay, so for a water or electricity system in Arizona, you might suspect that more frequent heat events may render certain components of the infrastructure more likely to experience failures. So what we're trying to do is assess specifically how everything from technological components associated with the extraction of water, the conveyance of water, the treatment, and ultimately the use and wastewater treatment of water are going to be impacted by more extreme heat. So will we see components of those infrastructure perform differently? We're coupling that with an institutional assessment of who are the players, the rules, policy, norms, and actors that have control over each of those technological components, as complex as that may be, ultimately to understand the sort of coupled infrastructural institutional vulnerability of these systems. And that's an ongoing WSC project that ultimately is the goal to develop a learning game where we actually are able to put infrastructure decision makers in front of a simulation of these coupled water and electricity systems and allow them to interact with these systems as they get shocked to see what is going to happen, and ultimately allow them to play this game over and over and over again to learn how to respond differently and proactively govern the system to avoid those perturbations that might occur in the future. The third project that we're going to talk about in detail today is related to questions of electricity reliability, which often has to do with water, particularly on the supply side. So here we're assessing the impacts to power generation, which Matt Bartos will talk about in much more detail, as well as transmission distribution, as well as changes in demand, those being the three pieces that we think need to be more rigorously understood to understand whether or not electricity will be more reliably delivered as things get warmer, as the environment gets warmer in the Southwest. And with that, hopefully that gives you a sense of the types of questions that we're asking, both the sort of technological as well as institutional vulnerability questions that we're asking related to extreme heat. And with that, what I'd like to do is give you guys a far more detail on the electricity reliability as it relates to water questions that we're asking, which have been led by Matt Bartos. Matt is a researcher at Arizona State. He finished his undergraduate about 1.5 years ago in environmental engineering and has worked as a researcher with me for about 1.5 years, leading a lot of these initiatives. And Matt is headed to the University of Michigan to their civil engineering program this August, where he'll do his PhD. So with that, what I'm going to do is hand it over to Matt to talk about the work that he's been leading on this component of the analysis. So can you guys check that Matt has audio?
This is Matt. Can everybody hear me okay? Okay. First of all, I'd just like to thank everybody for inviting me to this webinar, and hopefully I'll be able to show you something new today. So if anyone has trouble hearing me at any time, please just let me know, and I'll do what I can to fix it. Okay, so whereas Mike was presenting more of an overview of our general goals for our research lab, I want to take you into a specific case study on how electricity reliability may be affected under future climate scenarios. And I'm particularly going to be talking about power generation. So for example, how the achievable capacity at power plants is going to be affected by a changing climate. So as we know, the West is anticipated to get hotter and drier in the future. Well, much of the West, but particularly the Southwest. And as many of you probably also know, a lot of our power generation infrastructure relies on water resources. So we're not just talking about hydroelectric power here. So we're not just the power produced at dams, but also the electric power produced at, say, large baseload coal or nuclear power plants. So, under certain climate conditions, the generation capacity at these facilities may be reduced due to long-term changes in precipitation, stream temperature, air temperature, et cetera. So in the future, the generation capacity and therefore the electricity reliability in the West may be affected by changes in climate. So what we wanted to do is find out exactly how those changes are going to occur and to what extent they'll occur. So this isn't just speculation. This is something that actually has a precedent in history, especially over the past 20 years. So in 2003, there was a large heat wave in continental Europe in which more than 30 European nuclear power plants were disabled. Now this was caused because the water temperature was too high for them to meet discharge limits. So they had to either curtail generation or shut off generation in order to meet environmental regulations regarding discharge temperatures. Similarly, in 2007, a similar incident happened in the southeastern United States where many large coal plants weren't able to meet temperature discharge limits. And in 2001, drought in the Pacific Northwest caused a major electricity shortage due to decreased hydroelectric power capacity with an estimated damage cost of roughly $3 to $6 billion. So in general, what's happening is that in much of the United States, you're going to see less precipitation and higher water temperatures. Now, this isn't necessarily the case in all of the United States. For instance, in much of the Pacific Northwest, you may see more precipitation in certain parts of the year. But in general, lower flows and higher temperatures are what's anticipated for most of the United States. So I'm not going to spend too much detail on the methodology, but I at least want to show you how we produced the results that we did. So for each general type of generation technology, there are certain climatic factors that can affect the amount of achievable capacity. So for instance, for combustion turbine facilities, this is mainly like a peaking source of generation, which uses natural gas. It's only affected by air temperature. Whereas for open loop thermoelectric power plants, say large baseload coal and nuclear power plants, it can be affected by water temperature as well as the amount of available stream flow. So again, I'm not going to go into too much technical detail, but there are a number of physical models that we developed for each of these types of power plant. And each different type of power plant is affected by slightly different meteorological variables, meteorological and hydrologic variables. This is just a general overview of the modeling system that we used. So we used downscaled climate data, so downscaled climate projections, which we feed into a hydrologic model to come up with estimates of water temperature, projected runoff and stream flow, and then things like air temperature, humidity, solar radiation, et cetera. And if you want more detail on this, then I can answer that in the question session later on. So we start with the output from our global climate models or general circulation models, which are at a scale that is really too big to estimate what's going to happen at a particular location. They're generally at the scale of roughly 250 kilometers by 250 kilometers or 100 kilometers by 100 kilometers. So these climate projections, which are generally, like a temperature or precipitation, are downscaled using the BCCA method, or bias correctly constructed analog, to a resolution of roughly 12 kilometers by 12 kilometers. And these are what are fed into our hydrologic model. So we used a Vic hydrologic model, which is developed at the University of Washington, and a routing model that goes along with that, along with a separate stream temperature model, which uses a particle tracking scheme to estimate the temperature of water based on air temperature, radiation forcings, humidity, stream flow, and et cetera. So this is, all of our model outputs are at a resolution of roughly 12 kilometers by 12 kilometers. And we cover most of the Western Electricity Coordinating Council region, which is basically everything west of the Rockies. So the reason we chose such a large spatial scale is because the electricity grid, you can't really isolate what the reliability of a single state is, for example. So everything in this region is interconnected, meaning that if they're having problems meeting demand in one area, they can always route electricity from another area to meet it. So we looked at this entire area to be able to understand what the overall impact on electricity reliability for this interconnection is going to be. So what did we find? We found that under pretty much all of the scenarios, all of the climate model and carbon forcing scenarios, we see a roughly 1 to 3% decrease in summertime capacity by mid-century being 2040 to 2060. And in southern regions, you may expect to see capacity reductions of up to 5% just in an average year. So here's a map of individual power plants with expected reductions to capacity. And over here on the left side, we have just the reductions under different model scenario combinations. So we use 2 different GCM models and 3 different carbon emission scenarios. So you can see there's quite a bit of variance between them. But this map here is showing the average reductions in capacity, which is overall 1 to 3% of the total capacity in the WEC region. You can see that there's a lot of impacts occurring in California and the desert Southwest, which is due to both the generation mix in these regions. There's a lot of combustion turbine, which is affected by air temperature. And you know, it's expected to heat up a lot more in these areas, and there's predicted to be less precipitation as well. Whereas in some of the Pacific Northwest, where there's a lot of hydroelectric power, you actually see increases to capacity because under some climate model scenario combinations, you may see more precipitation, especially during certain times of the year. So southern regions are at the greatest risk. The Colorado River Basin, for example, average yearly capacity may be reduced from 30,000 megawatt hours to by about 500 megawatt hours or more. Whereas in the Pacific Northwest, you really don't see very much reduction in overall capacity. And that's mostly due to the prevalence of hydroelectric power and the fact that precipitation isn't really going to change that much. Here's just some annual plots of generation capacity over an annual basis. So 365 representing December 31st and 1 representing January 1st. And you can see that in the southwestern regions, there's a lot more capacity reduction during the summer than there is in the Pacific Northwest in particular, but the north, in the north, there's less capacity reduction in general. And thermoelectric generally suffers the greatest capacity reductions of any of the technologies considered. On a year-to-year basis, combustion turbine is the most affected, but steam turbine may see the most extreme reductions under drought conditions because it's largely dependent on how much water is available and what the temperature of the water is, and that can change quite a bit from year to year and from day to day within a year. And you can see if you just look at a time series, generation capacity reduces by quite a bit over the 21st century. So by mid-century, the impacts are pretty significant, but assuming a similar generation technology mix, by the end of the century, you may see even greater reductions. And I didn't really mention this a whole lot at the beginning, but renewable energy sources are generally less susceptible to changes in climate, although there's quite a bit of uncertainty in predicting the climate variables that affect these technologies. For instance, it's very difficult to predict wind speed at the resolution that you need to be able to make these kind of estimates. But if you just look at, for instance, changes in temperature, changes in air density that might affect these technologies, you see very small reductions in capacity. So while reductions of 1 to 3% may seem, it may seem like it's not that big of a deal at first, but under an extreme drought event, and we define extreme drought events as being one that may occur, say, every 10 years, you may see capacity reductions of as much as 8 to 9% for the fraction of generation that's vulnerable. And so utilities typically measure their reliability on a broad scale in terms of planning reserve margin, which is the fraction of generation, the fraction of available capacity left over after meeting demand. That's typically on the order of 15 to 20%, although it can go as low as 8 to 10% in much of the WEC region. So if you're talking about capacity decreases of 8 to 9% compared to the reserve margin of 15 to 20%, that's a pretty big deal. And currently, power providers aren't taking climate effects into account, especially not these kind of fine-scale estimates we're talking here. All right, and just to add some icing on the cake, basically this isn't impacts to power generation aren't expected to, just happen on their own. So during these drought events, or during the periods of the year where it's the highest temperature, you're also likely to see increases in electricity demand due to increased cooling loads, and also transmission capacity is expected to decrease as well, because typically transmission lines have a maximum operating temperature, and as it gets hotter, they're less able to dissipate heat, meaning that operators will typically reduce the current flowing through that transmission line in order to keep it at an acceptable temperature. So as temperatures get hotter, those transmission lines may see capacity reductions of 7 to 10% by the end of the century, and I believe, from like 2 to 4% by mid-century. So these three factors together can result in unreliable conditions, unpredictable conditions for the electric power sector. So what can we do about it? Well, transmission upgrades may be able to help route power from the less vulnerable regions to the more vulnerable regions. For instance, increasing the transmission capacity between the Pacific Northwest and the Desert Southwest may be able to help Southwest regions achieve better electricity reliability because the Pacific Northwest is less likely to be affected by climate change. Renewables are generally less susceptible to climate impacts, even though there's quite a bit of uncertainty surrounding what the potential climate impacts on renewables are going to be. But in general, they appear to suffer less climate impacts than conventional sources, meaning that by investing in more renewables, you can potentially mitigate climate impacts to the electric power sector. And finally, probably the simplest method for climate proofing our power infrastructure is just to install alternative cooling technologies to better deal with changes in climate. So for instance, combustion turbine facilities, there are certain cooling technologies, inlet air cooling technologies, which can basically offset any temperature-induced penalties that you may see. A lot of these just consist of evaporative cooling or mechanical chillers or things like that. And also upgrading open-loop cooling facilities to recirculating cooling facilities for large baseload power plants. That can also do quite a bit to mitigate the effect of climate change on power generation. All right, so I'm going to open it up for questions now. And please just type in your thoughts, and I'll do my best to answer.
Thanks very much, Mikhail and Matt. We are open for questions, as they said. One question I have while people are waiting to type things in is the following. What's your thinking about the climate scenarios themselves, since there is significant uncertainty associated with the specifications of the scenarios, and more importantly, in your context, it's not clear whether the temporal correlation structure of the sequences of temperature and precipitation produced by these models are reasonable. When you did your comparisons, did you account for that?
Could you rephrase that as just in 1 or 2 sentences?
Yeah, sure. So, do you account for the fact that the GCM scenarios of precipitation and temperature are likely quite different in terms of serial correlation structure than the real observations?
Right. So that is definitely one of the biggest sources of uncertainty for the study. And really, there's not a whole lot that you can do to improve like spatial correlation between precipitation and temperature for GCM models, other than to just use A, as many GCM models as you can, or B, to use the models that have the best performance in terms of their ability to match reanalysis data. So we did both. I mean, we used two GCM models, and both of those, well, for each model, we used three different three different carbon emission scenarios. And the models that we selected were based on their ability to simulate the ENSO cycle for the Southwest. And the ENSO cycle has a really big effect on precipitation and temperature in much of the Southwest. So we picked the Hadley Center's UKMO GCM model and the Max Planck Institute's ECHAM model, mainly on the basis of their ability to simulate the ENSO cycle, which
So another question, and then I'll pass you on to the people who are typing. So have you done purely ENSO phase analysis of this issue, like El Nino versus La Nina, using observations, rather than working with GCMs?
I'm sorry, I'm having a little hard time hearing you.
Oh, okay. So, instead of looking at climate change, you could just look at uh, whether the reliability is very different during El Nino versus La Nina versus neutral. And I wonder if you've done something like that or someone else.
Right. I mean, our focus for this study was just to assess long-term changes in capacity reductions, as opposed to, what the capacity reductions are going to be under a El Nino or La Nina scenario. It's fundamentally a study about climate change and its impacts on infrastructure.
Okay. Would it be possible for you to run such a scenario very easily?
Yeah, I mean, I suppose so. That wasn't really our focus for this study, though.
Yeah, no, I understand that. But the thing is that if you run it with real data, historical data corresponding to those conditions, many of the questions that come because of the GCMs would not be an issue.
Right, and that would be, I think, also an interesting study. But our fundamental question was one of, what long-term changes in electricity capacity are going to be as a result of climate change.
Yeah. So let me point you to the screen where there's a question. James Rising asks, does concentrated solar thermal suffer from the same problems as traditional thermoelectric?
Yes, its cooling system should be basically the same as a cooling system used by a traditional thermoelectric power plant. I think most of the concentrating solar power facilities in the West are typically ones that use groundwater, though, so they wouldn't be affected by changes in, say, stream flow or stream temperature. But technically, yes, they would suffer the same problems as traditional thermoelectric.
Okay. Then John Borg asks, are the capacity projections accounting for population changes in time and how demand might change?
This study that we just published was looking only at the supply side, so only at generation capacity. Although in a follow-up study that we're working on right now, we're looking at how changes in temperature may affect demand in the future.
Right. So I just brought the slides back one. So the three pieces that we're thinking about to answer this question of vulnerability of the electricity grid are generation, transmission, and then demand. So we are currently working on the third piece of demand and how certain changes in not only population but other characteristics in the region might affect demand relative to the supply losses that we just talked about.
Okay, and then Terry has a fairly long question, maybe easier for you guys to read it.
Do you have any response for this, Mike? Or
Yeah, I think, no, I don't have a response. I think this is beyond our expertise. So it's a great question. I don't know much about the technology, so I'm not able to comment.
Then we have John Board again. Where do you see the most innovation happening? Examples of specific power plants, municipalities.
well, there's there's quite a bit that's being done, at least in the Southwest, to deal with potential water scarcity issues. For example, the Palo Verde power plant here in Arizona has for a long time been using wastewater to cool its, to cool the process steam. There's, some measures that are taken from time to time to deal with water scarcity as well. So for example, in Navajo Power Generating Station, they've had to lower the intake pipe depth for their power plant to be able to intake water from the Glen Canyon Dam reservoir. But I think that using more wastewater to treat, I'm sorry, using wastewater to meet cooling requirements for power facilities is a good idea if it's feasible for the particular project. I think that, like I said, installing inlet air cooling systems for combustion turbines could also go a long way to helping mitigate climate impacts. And I think also having more storage capacity on the grid could also do quite a bit.
Next one is from James. Did you look at the potential for renewable generation facilities as an offsetting factor during the periods when traditional generation methods suffer the greatest impacts?
Right. So we didn't, look at it in too much detail, but typically the times when traditional facilities suffer the greatest impacts are during basically the middle of the day, during the periods of highest air temperature. And that's also typically the time when solar facilities see the greatest, when solar photovoltaic facilities have the greatest capacity. So yes, I think that would be an offsetting factor.
So one other dimension here is that another potential variable with uncertainty is the generation mix into mid-century, which is the kind of rough time frame, 2040 to 2060, when we did this study. And Matt and I looked into this a lot, and the Energy Information Administration publishes some forecasts of what the mix will look like, both in the WEC as well as in the United States, out till mid-century. And while renewables do gain market penetration, and there is a significant increase in the amount of capacity from renewable technology deployment, thermoelectric and traditional electricity generation technologies constitute a dominating share even to mid-century, where coal in terms of megawatt capacity remains roughly the same. Natural gas increases under the assumption that gas prices will continue to fall. And renewables, while they do increase, do not command a dominating share of the mix according to the EIA projections by mid-century. So there is this somewhat confounding, or there is somewhat a concern of whether or not renewables will exist in any major capacity to offset some of the impacts that we're estimating by mid-century.
Question from James Rising. Do you see a scenario with cascading failures between electricity and urban water use, for example?
Yeah, so James, this is our WSC project. So I kind of alluded to this and gave a 40,000-foot overview early on in the talk. So we're asking this question and trying to address this question right now by looking specifically at the Arizona water and energy system. So Matt gave you the overview of the electricity side and the impacts that exist there, or the potential for impacts that exist there. On the water side, we're thinking about similar questions, but more for both systems from the component level on up. So the potential impacts of higher temperatures on pumps and pipes and specific components, treatment technologies, and so on, as well as on the electricity side. What are the capacity reductions? What are the chances for increasing maintenance in certain components or increasing failures in certain components? And what we're doing to answer your question, I don't have the answer just yet, give us a couple more years, but what we're doing is developing a event tree failure analysis framework, a probabilistic model that allows us to capture the likelihood or the increased likelihood of a cascading failure within each of those systems and across those systems. So if there's a failure in the electricity grid like we saw in the Northeast in the mid-2000s, does that have the potential to significantly disrupt water systems in a way that we don't have reliable provision or decreased supply, I should say, of water, specifically related to increased temperatures. So can we come up with a scenario in which we do have a cascading failure that occurs across those systems? Hypothetically, we can. Whether or not that's realistic is what we're trying to assess right now. The other, I think, important dimension of that is that these failures, I think, are not purely technological failures, as we saw with the Northeast blackout in 2003, where a downed power line in First Energy's territory in Ohio led to, although there was redundancy with that line, led to a cascading failure that ultimately left, I believe it was 50 million people in the Northeast without power, from Pennsylvania to New York to New Jersey and so on. So what we saw there is that engineered systems, we've engineered a lot out of the major ways in which engineered systems can fail, and there are opportunities, I think, for kind of institutional failures, specifically that institutions in this case are not necessarily prepared to deal with more frequent outages or more frequent downages of certain components in the system as they relate to more exposure to extreme heat. So what we're trying to do is combine these sort of potential for technological failures, maybe a pump going out more frequently because it wasn't designed to the tolerances that, or doesn't have the tolerances in design that we might need it to have with more frequent heat exposure. So that's one piece of it, but the other piece is are the many institutions that manage water and electricity systems ready to respond to these more frequent outages, and if not, what do they need to do?
James is typing again. Let me ask, when you did the analysis of um, the 10-year drought that I think is on the previous slide, right about here, yeah. Have you run anything with historical data to see whether the margin that they predict, which is 15 to 20%, holds true over the historical period, or how it behaves during protracted droughts?
The numbers for the historical period are just averages. So the 15 to 20% is just for an average year.
Right.
So in looking at capacity decreases under 10-year drought conditions, for instance, we're comparing the capacity reduction under a 10-year drought to the planning reserve margin for the historical period.
Right, but that is
Um,
not a fair comparison in any way, right? Because you want to look over a certain history and figure out the probability with which the probability distribution of the margin basically in two different cases.
right. Um, so yeah, I mean there have been periods, uh, in history where the planning reserve margin has gone, say, below 5%. So for example, in 1998 in California, uh, there was a huge heat wave, and combustion turbine facilities were um, significantly impaired, and the California Energy Commission, for example, uh, you know, had to announced that, certain customers had to curtail their loads because they were at a PRM of under 5%. So that does happen during the historical period. We are just showing that under the future period, with expected changes in climate, that those events are likely to become more severe and more frequent.
Thanks very much. A very nice project, and love to hear your talk. And let's hear any more. Otherwise, I think we are done for the day. Okay, well, doesn't look like any. Amir is typing now. Okay, thanks. Okay, thanks very much, guys. We would love to stay in touch with you and see how we can collaborate.
Thank you all for the opportunity to speak.
Thank you.
Okay, bye.
Bye.